Okay, welcome back to Sketching the Graph Part 2. We're still working on example number 5 on page 15 in your notes. And we had just found our critical values, our critical points. And using the second derivative test, we determined whether they were maximums or minimums. And here's the result right there. Now make sure you're writing these points down. All of these points had to be plotted. Notice the y value here is kind of big, like it's 20. Well, in order to plot that point accurately, you're probably going to need to scale your axes somehow, okay? With your graph paper, you're going to need to scale that. And anyway, let me just come down below here now, some more blank space. What we have not yet done, let me just go back up and look at the second derivative, is 12x plus 6. So y double prime equals 12x plus 6. Now, if you want your point of inflection, remember, you set the second derivative equal to 0. So what you're going to end up with there is 12x plus 6 and equals 0. 12x equals negative 6. Divide both sides by 12. And, ooh, look at this, you get a fraction. So x is actually equal to negative 1/2. And that's quite possible sometimes. You may get fractions or decimals for points of inflection or even for intercepts, things like that. Actually, our intercepts in this question were x-intercepts were 2 decimals because we had to use the quadratic formula. Okay, so anyway, I'll also tell you now, if you put that negative 1/2 back into your equation, you're going to end up with y is equal to, and I'll just tell you what it is. It's actually 13/2, so another decimal or a fraction. You can call that negative 0.5 and 6.5 when you make your graph. Okay, so now step number 5, we have to use the second derivative test to determine the concavity. And this is basically just going to reinforce the fact that we think this is a maximum and we think this is a minimum according to our calculations. We think this point right here is going to be a point of inflection. So what's going to happen is your concavity table is actually going to tell you that. So we only put the point of inflection in there. So here and here, the point of inflection was negative 1/2. That was your x value. Remember, that's what goes in the top row. And then in the second row, it's f double prime. The concavity test requires the second derivative. Now you know this is going to be a 0 there because, well, that's how you calculated it, right? It gave you a 0 for your second derivative. So that part is not going to be a max or concave up or concave down. Now pick a number a little bit less than negative 1/2. Well, how about negative 1? A number a little bit more than negative 1/2? Well, let's try a 0. So put those into your second derivative right there. And if you put in a negative 1, you're going to get back negative 6. And because the second derivative is negative, that means that it's concave downward. That's where it's concave down, when x is less than negative 1/2. And if you put a 0 into your second derivative, well, 12 times 0 plus 6, that's going to give you a positive 6. Positive, so it's concave up. So we can tell that the graph should be concave down when x is less than negative 1/2. That was our point of inflection, remember, from there down. And it's going to be concave up when x is greater than negative 1/2. And that would be this part right there. So what you're ready to do now, you have all of your information, you have all of your points. You should now take a piece of graph paper, put your 2 axes on it, scale it however is necessary so that you can get all of your points in. Sometimes you may want to make the scale smaller. Sometimes you may want to make the scale bigger. Now, I happen to have the solution to that, by the way, here. And so what I'm going to do is just bring up the graph and show you what it would look like. And here it is. Now, this was done. I didn't draw this one by hand, obviously, but I did use a graphing program for this. Actually, I think I may have even used Desmos for this. But now you can clearly see that your 2 x-intercepts, here's the first one. Oops, I should get my marker for this. Maybe I can't get my marker for this. But anyway, you can see the x-intercepts negative 3.310, which is what we calculated. And on the other side, positive 1.810. There's 0, 0, the origin. That's an x-intercept and a y-intercept. And yes, we certainly did get a maximum at -2 and 20. And we did get a minimum at 1 and -7. Again, note the scaling. Note the scaling on the graph. I actually made the scale bigger for the x-axis because I wanted to spread the points out. You don't want your points all clumped together in one area. You want to space them out nicely. And the y-axis, actually the scale was made smaller because we had to go up as far as 20 on one side and we had to go down to -7 on the other side. You can pick an appropriate scaling on your own. You may not all use the same scaling, and that's fine as long as your graph has some scaling there that's consistent and your points are plotted correctly. All right, so that's it for example number 5 on page 15. There's another example there on page 16, example number 6, and this one is actually a little more complicated than anything I would probably give you on a quiz or on a test. Have a look at this. This is a 5th degree polynomial equation. All right. Now, it's simple enough. It's fairly straightforward. It's not that difficult to get your x-intercepts and your y-intercepts. Then to take the first derivative, set the derivative equal to 0, and you'll get your critical points. Put those back into your equation to get your y values. Taking the second derivative is also fairly straightforward. Here's a heads up for this one, though. You're going to have 3 points of inflection here. Kind of unusual, but that's exactly what's going to happen. You're going to have 3 points of inflection. And if you did decide to go ahead and graph this one, now let me see, can I bring that up? Maybe I can. No, wrong way. If you did this question, there's the workings there, but remember now, all of this is on, no, wrong way. All of this is posted on D2L. And there's the example there. And here's what the graph is going to kind of look like. Now look at that. Pretty exotic, isn't it? But there are 3 points of inflection. There are only 3 x-intercepts. One of them is what we call a triple root. Triple roots tend to flatten out at the x-intercept. And you can see a maximum point there, a relative maximum of -1.55, 5.95, and a relative minimum of +1.55 and -5.95. So have a look at that one, and also try the practice questions on pages 17 and page 18. Try those as well. Let me know if you have any trouble, and I might even look at this one a little bit further, this example right here during our class. Okay, so thank you so much. We'll be starting topic number 7 very soon, so please print off the notes as soon as you have an opportunity for topic 7. And I'm also going to get out an assignment very soon, maybe in the next day or 2. Okay, thank you very much. Bye-bye.